Question 51 asks to give the number of lone pairs around the central atom and the molecular shape of SCl2. So we're going to start out by drawing the Lewis structure. We have sulfur in the middle. We add up our valence electrons here. We have 7 times 2 for the 2 chlorines plus 6 for the sulfur, gives us 20. We subtract 4 for the 2 single bonds already made, leaving 16 behind. Fill up the outer octets, 2, 4, 6, 8, 10, 12. Leaves 4 electrons, which we place on the central atom in pairs. 2, 4. You can double check the structure now to make sure everything has a full octet. And yes, every atom does. You can also calculate formal charges on each atom, and every atom has a formal charge of 0. So this is the best structure that we can draw for SCl2. We would say, first of all, this has 2 lone pairs on the sulfur, which is the central atom, answering the first part of the question. The second is the molecular shape, or the molecular geometry. So we would say that this is an AX2E2 compound because there are 2 bonds, 2 atoms, and there are 2 electron pairs. And this would have 4 total electron groups, which would give an electron group geometry of tetrahedral with bond angles of 109.5. However, this is looking for the molecular shape, which we would call bent. Question 52 asks for the ideal bond angles in KrF4. Start out by drawing the structure again. Central atom is krypton with fluorines all connected by single bonds. If we add up our valence electrons, we have 8 for the krypton plus 7 times 4 for the 4 fluorine atoms equals 36. We subtract 8 electrons for the 8 single bonds, which leaves 28. And we use those electrons to fill up the octets of the outer atoms first. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Leaves behind 4 electrons, and the leftover electrons goes on the central atom, which is the krypton. 2, 4 minus 4 is 0. We can now double check to make sure everything has at least an octet, and that is the case. And we should make sure that everything has the lowest formal charges possible, and everything here has formal charges of 0. So we have the structure that we want. This would be an AX4 for 4 atoms attached to the central atom, E2 for the 2 lone pairs. Total of 6 electron groups would give us an electron group geometry of octahedral. Octahedral would give bond angles of 90 degrees. This one would lose 2 atoms, right, because it has 2 lone pairs, so the actual shape that this thing would take on is what we would call square planar, which would look kind of like this. If you have a lone pair on top and on bottom, we would have all atoms in the exact same plane. So it's flat, all the bond angles are right angles, and I guess fluorines on opposite sides would also be 180 degrees from each other if you want to be super complete. Question 53, what are the real bond angles in SOCl2? Like always, we start by drawing the structure, SOCl, Cl. We have 6 for the oxygen plus 6 for the sulfur plus 7 times 2 for the chlorines. That equals 26. Minus 6 for the 3 bonds is 20. Fill up the outer octets. 2, 4, 6, 8, 10, 12, 14, 16, 18. The 2 remaining electrons go on the central atom, which is the sulfur. We check to make sure everything has a full octet, and yes, everything does. Next, we check formal charges, and if you calculate the formal charges for all of the atoms, the chlorines end up with formal charges of 0, but the oxygen has 6 valence electrons minus 1 bond minus 6 electrons is -1, and the sulfur has 6 valence electrons minus 3 bonds minus 2 electrons is +1. So our charges on this atom would be negative and plus. So we would like, if possible, to eliminate these formal charges, and we can actually do so by making a double bond between the oxygen and the sulfur using a pair of electrons from the oxygen. Now that would cause the sulfur to exceed its octet. If we bring one down here, what we would end up with is a structure which looks like this. Chlorines have full octets. Sulfur still has a lone pair. This reduces all the formal charges to 0. As I said before, it does cause the sulfur to exceed its octet, but that's okay for sulfur because sulfur is in the 3rd row. If it's in the 2nd row, you can't go above the octet, but for sulfur it's okay. And it's best to exceed its octet if it allows you to reduce the formal charges. So we have 4 electron groups here. This would have an electron group geometry that's tetrahedral, which has bond angles of 109.5 as the ideal angles. However, this is asking for the real bond angles, and we don't want an exact number when we ask for real bond angles. We just want to know, is it greater than, less than, you know, that sort of thing. And in a molecule like this, what would happen is the lone pair of electrons that's here is more effective than the single bonds at repelling the other electron groups. So we would expect the bond angles in this compound to be a little bit smaller than 109.5. You can kind of think of it as maybe looking like this structure up here on the top right, where you have sulfur, a lone pair, Cl, Cl, O with our electrons, with these bond angles being slightly less than 109.5. Second part wants CH2O, which is formaldehyde. We get carbon, oxygen, hydrogen, hydrogen. Add up your electrons. You have 4 for the carbon, plus 2 for the 2 hydrogens, plus 6 for the oxygen is 12, minus 6 for the 3 bonds is 6. We fill up the octets of the oxygen. We take 1 electron pair down so that carbon can have a full octet in the middle. And that gives us carbon, oxygen, hydrogen, hydrogen. This is AX3. We would say this is trigonal planar. We would expect ideal bond angles of 120. However, one of these 3 bonds is a double bond, which is more effective at repelling the 2 single bonds than the single bonds are. So this bond angle right here would be a little bit less than 120 degrees, whereas this bond angle would be a little bit above 120 degrees. This question asks for which one of the following molecules does not have a dipole moment. And these questions are really looking at the geometry of these compounds, which you have to determine by first doing the Lewis structures. We just did the Lewis structure for A for the previous question. If you remember, was this. And this will have bond angles, or sorry, bond dipoles, which will not cancel out. The carbonyl, the C double bond O, is very polar, big electronegativity difference between carbon and oxygen, and the carbon hydrogen are also polar but less so. This molecule will have dipoles that do not cancel if you add the dipoles together, and we'll have a net dipole that's pointing in that direction. So that is not the one we're looking for. For compound B, if you draw out its Lewis structure, you get a structure that looks like this. And I'm going to just, for the sake of time, spare you some of those steps. And it turns out that a pH bond is actually extremely weakly polar, in the sense that the electronegativity of hydrogen and phosphorus is almost identical. However, there will be a weak dipole moment, and because of the shape of this molecule, because it's not symmetric, those dipoles will cause a very, very, very small net dipole. For that compound. For C, we have SH2, which has this structure. This is bent. We have a bond angle that ideally is 109.5. The real bond angle will be smaller than that. And we have, again, bond dipoles that will not cancel out because the shape of this compound is not equally symmetric all the way around. Okay, if you had bond dipoles that looked like that, for example, we would have a net dipole pointing up as well. For D, the correct Lewis structure for D has a structure that looks like this. CS2, carbon disulfide, has two bonds, and this would be AX2, and this would be linear. The bond angle is 180 degrees, and we have bond dipoles that are pointing in opposite directions and of equal magnitude, so those cancel completely, so that the compound will have no net dipole. Which looks like the answer to the question, but let's just do E as well. C, hydrogen, hydrogen, Cl, Cl. This has 4 electron groups around the carbon, so this will be tetrahedral. I spelled that wrong. Trahedral. Bond angles of 109.5 degrees. And this will have bond dipoles that are pointing in directions that do not cancel out. We'll have a net dipole moment for this compound as well. Next question. Arrange the following substances into order of increasing boiling point. So we want to go from lowest to highest. I usually think about these questions the other way around, but that's easy to fix for sure. The highest one here is going to be the methanol, because it is the only one out of the group that has hydrogen bonding. Second highest is going to be CH3Cl. This is a polar molecule. It has a structure that looks like this. Hydrogen, hydrogen, hydrogen. It's tetrahedral. It'll have a net dipole in this direction. That means this has dipole-dipole, intermolecular forces, which aren't as strong as hydrogen bonding, but they're stronger than nothing, or stronger than dispersion at least. So that'll be number 2. And the last two, O2 and N2, are completely nonpolar. And the difference between these two has nothing to do with the fact that it's a double bond or a triple bond. What we look at here is the total number of electrons in the compound, because both of these have only dispersion. And dispersion forces get stronger the more electrons the compound has. So O2 has more electrons than N2, so O2 will have a higher boiling point than N2. So starting from the lowest to highest, it would be N2 first, O2 second, CH3Cl next, and then last methanol. increasing in that direction. What is the hybridization of sulfur in SO2? Again, we draw the Lewis structure. Sulfur, oxygen, oxygen. Our number of electrons is equal to 6 plus 6 times 2 is 18, minus 4 for the two double bonds is 14. Fill up the outer octets first. That took 12. We have 2 electrons left to go in the central atom, which is the sulfur. We do not have a full octet on the central sulfur, so we need to move 1 electron pair down. So let's use these ones here. We're going to erase them and make a multiple bond. So we're closer. However, this structure still isn't ideal because we have formal charges on the oxygen of -1 and the sulfur of +1, which we can eliminate by taking another pair of electrons down. So if we do that, take that other pair of electrons down, that gives us a double bond here. We can't forget to erase that electron pair that we moved, and that removes the charges as well. So we end up with this structure. We would say this is AX2E. We have 3 electron groups, which means the bond angles ideally are 120 degrees. With 3 electron groups, we know the central atom has to be sp2 hybridized. You can think of sp2 as orbitals that are made from 3 atomic orbitals. There's an s and 2 p's. And the number of orbitals that goes in to make the sp2 is equal to the number of electron groups around the central atom. 57, according to VSEPR theory, identify the orbital overlaps in the following molecules. We have S and O in SO3. I'm going to speed through this just a little bit and give you the Lewis structure. We're using the exact same procedure we used in all previous examples. It looks like this. The central atom has, again, 3 electron groups, which means it's sp2 hybridized. So it wants to know, for that double bond between a sulfur and an oxygen, what the orbital overlap will be. Well, think of this bond as being composed of a sigma and a pi. And also remember that terminal atoms do not hybridize. So the oxygen is going to use its p orbitals. So the single bond, the sigma, is made by taking a sulfur hybrid orbital, sp2, and overlapping that with an oxygen p orbital. The pi bond, and I think all pi bonds you will ever see in this course, are made by the overlap of 2 p's. So we'll have a sulfur p and an oxygen p, which gives us our bond in the center. So that's what we're kind of looking for here. The last one says, or the second one, between nitrogen and carbon in HCN. The Lewis structure for this is carbon, nitrogen, like so. And it wants it between the N and the C. This has a triple bond, which is a sigma plus 2 pi's. The carbon has 2 electron groups, meaning it's sp hybridized. 2 orbitals make an sp, an s and a p. And 2 is equal to the number of electron groups. So the sigma bond is made by taking a carbon sp and overlapping that with the nitrogen p. Remember, the nitrogen is terminal here, so it does not hybridize. The 2 pi bonds are made from a carbon p and a nitrogen p, carbon p, nitrogen p. And what this would sort of look like, let's see if I can use my art skills here. So you'd have your carbon. It would have an sp orbital that looks like that. We'd have another sp orbital on the other side, sp. The hydrogen only has a 1s. The nitrogen has a p. We call that the pz, where one phase of that can overlap with the carbon to form your sigma bond. The carbon will also have some p orbitals of its own. It'll have that one, which will overlap with a p orbital, second p orbital on the nitrogen. That should not have been filled in, so those kind of overlap this way. These ones overlap that way. And lastly, we have another p orbital on the carbon and on the nitrogen. Here and here. Those will overlap in back. These will overlap in front. And that's it. The nitrogen has one more orbital that we haven't talked about, and that is its s orbital. 2s. And that would be the orbital where we would find the lone pair in. All the question really asked for was this stuff here, though, so that's just bonus, I guess. Question 58. A molecule containing a central atom with sp3d2 hybridization has a what electron group geometry? Well, sp3d2 is made from an s and a p and another p and another p and a d and a d, which is a total of 6 orbitals. That means this compound has 6 electron groups. And if it has 6 electron groups, that must mean it is octahedral. All right, we're out of the Lewis structure stuff and into the acid-base questions. First one, what is the pH of a 0.050 molar HBr solution? This one is a strong acid. You need to know your strong acids. I believe there's 6 that you have to be aware of. HBr, HCl, HI, HNO3, H2SO4, and perchloric acid maybe, HClO4. Probably the ones you need to know. What is the pH of HBr? So the fact that it's a strong acid means it's going to dissociate completely in water. So our HBr is going to react with water. We use arrow to the right. We do not use an equilibrium arrow here because we have a strong acid on the left. Strong acids go 100% to the right. This makes H3O plus and Br minus. So if 100% of our HBr solution dissociates, once it's done, we're going to have an H3O plus concentration of 0.050 molar. Our pH is the minus log of that H3O plus concentration, is the minus log 0.05, which is 1.30. The next question asks for which of the following is considered to be a Lewis base. A Lewis base is defined as something that can be an electron pair donor. So what does something need to have in order to be an electron pair donor? Well, it needs to have an electron pair, in particular a lone pair. So we look at all the structures on the left and pick out which one has a lone pair. And the only one that does here is water. It has the structure that looks like this, which you're probably familiar with. It's 2 lone pairs, and that's it for question 60.